we had finished the time with this slide on Monday. I want to point out again that the idea was that this individual by the name of Ernest Rutherford had come up with this now almost universally applied model of the structure of the atom. It's called the planetary model because the experiment he performed showed there was a lot of empty space in atoms, just like there's a lot of empty space in our solar system. And there's a massive center of the atom, just like there's a massive center of our solar system. And at quite some amazingly far distances away from that massive center object are orbiting satellites. In the case of the solar system, of course, they are the planets, but in the case of an atom, they are the electrons. And there's a difference, of course, between the attractive force that binds the solar system, that is gravity. Here, the attractive force that binds the subatomic particles together is positivity and negativity. There is one caveat, though, and this is one of the still somewhat riddling questions of nature, just how in the world this nucleus really works. The nucleus is where all the positive charge is located. And by the rules with which we understand the way the universe works, these charges should be repelling one another. So Rutherford had to propose there was something else helping to hold the nucleus together, and he could tell there was something in there because there was of the way the mass of the atoms grew as you put more and more charges into an atom. He could tell that there was something that was not quite fitting his pattern of recognizing the behavior of atoms. And so he proposed that there was a non-charged particle that helped to bind the nucleus together, which he called the neutron. Okay, so then on this slide, we had showed these values before, and I had mentioned at the end of the period, the very end of the period, the fact that I'm listing the charge on the proton and the electron in the second column in that table, such that they are exactly numerically the same in value to 3 digits of scientific notation. They are actually numerically the same to all digits in actuality. This is not only in terms of our ability to measure the number, but also in terms of what we predict theoretically. The theoretical prediction is that these are equal and opposite charges of these proton and electron. And as a matter of fact, the other thing of great importance is that it is the smallest amount of charge allowed in the universe. You cannot take an electron, chop it with a hatchet, and get half the amount of charge on one piece and half the amount of charge on another piece. Charge does not come in any smaller increments than is present in the electron or the proton. Now, of course, as we know, this is a number that is so tiny that scientific notation form means you should put a decimal point, 18 zeros, and then 1 6. So this is an incredibly small number. And it's so incredibly small that what we would claim is charge is essentially continuous. 2 electrons would have a charge of negative 3.2 times 10 to the minus 19. 3 electrons would have a charge of negative 4.8 times 10 to the minus 19 coulomb. So every time you add an electron in, you just build the charge up. But since these charges are so small, it just seems like the number scale of charge is essentially just a continuous range of charges that are possible due to the tiny nature of these. Okay, now the other thing that has been measured for these is their masses. Their masses are given in the SI unit of mass, which is the kilogram, and that's what physicists have chosen to use to measure mass in, so that's what these are listed in. You can see that these are absolutely tiny masses of these particles as they are listed there. Now, what I do want you to note is that protons and neutrons are well over 1,800 times heavier than electrons. Electrons are way tinier than either of its cousin subatomic particles. The other thing you should probably note there is that in the 4th digit a neutron is slightly more massive than a proton. The proton and neutron don't match mass exactly. There's a slight difference in them. And this goes directly to our understanding of really what a neutron is. As far as we understand, a neutron is a combination of a proton and an electron. They're married together and their charges essentially cancel, so they are net zero charged entities, and it has a slight more mass than does a proton because electrons are much lighter than protons. So when you add the electron in, it only varies the mass to a very, very tiny amount. Now, again, as I pointed out, the charge on the proton and the electron are exactly opposite. And I tried to point out to you the nature of the sign of the charge on the proton and the electron. We always say that electrons are negatively charged. We always say that protons are positively charged. And charge in our universe comes in two, if you like, flavors. That's what I would prefer to think of them as. I have flavors of charge. There's a number measurement on the charge, and now there's a sign indicating which class of charge you happen to fall into, the negative type of charge or positive type of charge. Now, the deal is that, and this is something that we should know, and we probably already do know, is that opposite charges are attractive to one another. Pluses pull on minuses, minuses pull on positives. So if two bodies have opposite charges, they exert an attractive force on one another. Now, if two charges that you have somewhere laying around are of the same sign, or I could say they're the same flavor, then they have repulsive character relative to each other, meaning they will try to push each other apart. So a negative charge around a negative charge has forces that push outward from each other. A positive charge around a positive charge will exert forces that push outward from each other. On the other hand, a positive charge and a negative charge will have forces that pull inward towards each other. And this is the nature of how all of matter is sticking together. It's the opposite nature of the charges that make up the matter that constitute all animate and inanimate objects in our universe. Okay, now I mentioned this again, and I will say it just for the last time. The reason really that the sign is required when we're talking about charge is the fact that the charge can either be attractive or repulsive. Really, that sign is kind of giving you an indication of direction, just like the number scale. I can start at 0 and have positive numbers that say head to the right on a number line, but then the negative numbers grow in magnitude to the left. If the positive numbers are growing in magnitude to the right, the negative numbers are growing in magnitude to the left. So it's sort of the same idea. I'm assigning this flavor to charge, a positive or negative. It's either a push that charge is going to experience due to another one, or a pull that charge is going to experience due to the other one. So I have a plus or a minus action based on the type of charge that is being exposed to another charge. Okay, now I mentioned this, but I want to say it again one more time. What holds the universe together depends on how massive the particles are. Gravity only rears its ugly head as objects become extremely massive. As a matter of fact, you and I have gravitational attraction for each other. Me and this roll of paper towels have gravitational attraction to one another. But since my mass and the towel's masses are so small, the pull that is exerted between me and the pot and the towels is so small that I don't even really feel it in the towels as I put them closer or further away from me. I can't really sense how much pull there is because it's such a small pull. Now, compared to me and the Earth, though, the Earth is so massive that there is a huge pull that I experience due to the Earth. And there is a huge pull that the Earth experiences due to the sun. And there's a huge pull that the moon experiences due to the Earth. It's because these are extremely massive bodies. Now, charge, on the other hand, the attractive force between charges is huge compared to the amount of charge they possess. So the point would be that objects have to be incredibly massive before the gravity pull on them is any way, shape, or form measurable. However, only tiny amounts of charge are necessary before the attractive force of their pulls are noticeable and measurable. So the electrostatic, as we call it, attraction is much stronger force in the universe than gravitational attraction, because you only need very small charges to get substantial electric push and pull, whereas you need incredibly large, massive bodies before you get gravitational push or pull. So what we would say then is all the cells that constitute us are of course made up of atoms, and the atoms are of course made up of charged particles, and these particles have mass. Well, the atoms that are in our bodies are not held together in cells because of the gravitational attraction between the atoms in the cell. The atoms in the cells of our body are held together by the electric attractions that they exert upon one another, because that's a much more powerful force. This wall here, if I try to push on this wall behind me, I can't knock it down because there's a huge amount of attractive force between the particles that make up the wall. They are, of course, have mass to them, so they have gravitational pull on one another. However, that is very, very tiny due to the individual particles that make up the wall. How massive they are does not lead to much gravitational pull between them. However, they are also charged particles, so they are held together very tightly due to that charge that they possess. Okay, so the bad news is that Rutherford's beautiful planetary model, and I'm going to quickly pop back here and show it to you. The planetary model of Ernest Rutherford, even though it's listed in every textbook from grade school through college, is just a model. And there are significant issues with Rutherford's model. And the significant issues begin with the fact that it models the atom with charges of the electrons circularly orbiting the central nucleus. And just like the Earth, every 365.25 days goes around the sun once, we're saying then every so many seconds, the electron would orbit around the nucleus. By the way, you notice I said that the time it takes the Earth to go around the sun is actually 365.25 days, because every fourth year, if we don't add an extra day into the calendar starts to get screwed up. So really, there's an extra quarter a day a year, then the year actually fits into days. 365 and a quarter days later, we're in exactly the same spot around the Earth that we were 365.25 days before. So, interesting little note that the year is really not 365 days long. But in any event, if we now use Rutherford's model and we take it for granted that that's the way that electrons behave around the nucleus, it turns out that if an object is circularly moving in space, that means it is accelerating. That means it's changing velocity. Anything moving in a straight line at the same speed is not accelerating. As long as your speed is the same and you're moving in a straight line, you are not experiencing any change in velocity. If you're moving at the same speed, but you're curving, even though your speed is the same, you're constantly changing the direction of your motion. That is an acceleration. So anything that flies in an arced path is accelerating. For instance, when I shoot a gun, the bullet takes a parabolic trajectory. And that's because it's moving with some velocity through the air, but it's also being pulled by the gravity of the earth so that it's curving its motion. And the acceleration that the bullet would experience is F equals ma, a very familiar expression. And the F is the gravitational force causing the acceleration or change in direction of the velocity of the bullet. Now, likewise, we can pretend now for an electron, if it's moving circularly around the nucleus, even though if it's moving at the same speed as it moves circularly around the nucleus, it is accelerating because it's changing direction constantly to keep in a circular path. So there's an electrostatic force pulling the electron inward, which is causing it to move in a circle. Well, what physicists understood was anytime charge accelerates, it should radiate, meaning it should give off electromagnetic waves. Maybe they would be in the microwave region, maybe they'd be in the radio region, infrared region, but changing velocity or accelerating electrons that are charged should make them give off light beams. And if you put detectors on atoms, you can't detect these light beams. So they had to eliminate the fact that electrons were moving in that fashion around the nucleus. And also, if they are radiating, they're losing energy. And just like something orbiting the Earth, if it loses energy as it orbits the Earth, it begins to spiral inward and inward and inward, and then it gets trapped by the Earth's gravity and gets pulled straight down to the planet. So if an electron was truly accelerating by curving as it traveled around the nucleus, it should be radiating, and as it radiates, it should lose energy, and then it should eventually crash into the nucleus, which never happened. So they needed a new model. Even Rutherford's model wasn't good. And we're not going to do a whole bunch with this new model, but I want you to certainly know the name of this model. It is quantum mechanics. Quantum mechanics is a completely different story as to the structure of an atom than the plum pudding model was or than the planetary model was. This is a wholly mathematical model that was devised by a bunch of scientists in the early 1900s. And they went and tested the model that they applied mathematically. They didn't have experimental evidence of this behavior other than there was no radiation coming from atoms and there was no crashing of electrons onto the nucleus. So they knew by the scientific method something was wrong in their hypothesis. So they made a new mathematical model and attempted to test it. And the mathematical model they made is now known as quantum mechanics. So on the next slide, I just say a few things about the weirdness of quantum mechanics. Now, let me tell you, to understand quantum mechanics fully would require a lot of investment of your time and energy. As a matter of fact, I'm trained in quantum mechanics, and it took me about 12 years, I would say, to learn all the physics, the mathematics, and the computer programming to understand what quantum mechanics really means. It's out there, we will say, out there. And what quantum mechanics boils down to, I can summarize with 3 simple statements. Quantum mechanics essentially meant that electrons do not behave like normal matter. When they're in an electron, when they're in an atom, they are not like little hard spheres, little tiny hard spheres of negative charge at all. So what we say is they don't have particle character. If they were matter, if electrons were truly matter when they're in the electrons, or when they were in an atom, excuse me, they would each have to take up their own space. Just like I'm showing in this cartoon here, that, where's my, well, I thought I put some words on there. I guess I didn't. I thought I put some words by the bricks that say, every brick you see in the picture is taking up its own space. So what electrons are really doing when they're in an atom is they're not behaving like matter. They are behaving like waves. Now, you probably haven't thought a lot about the difference between wave behavior and matter behavior, but it's really fundamentally different. One of the important things that waves can do is that they can simultaneously occupy the same place at the same time, exactly the same place. You can have a wave in the same position as another wave, and they can just pass right through each other and don't care about each other. As an example of that, I show a cartoon of some people having a conversation. And we've all been in conversation with more than one other person at the same time. You can hear everybody. You can hear each of these individual people talking. Now, it might get a little garbled when too many people start talking simultaneously, but you can certainly make out each individual sound that each person is making. And this is it despite the fact that the sound that they're making is waves. And the waves emanate from these individuals, and then they all come together and culminate in your ear. So there's some point at which these waves, as we say, superimpose on one another. They all pile up together and all come to my ear, yet I can differentiate them individually. Same thing is true with color. Everything in this room has a color associated with it. Light comes from a source, hits the object, bounces off the object, and then comes into my eyes. And as I look out around the room, I can see all the objects in this room, and the colors from all of these objects are simultaneously impinging upon these tiny openings in my eye. And guess what? All these waves are able to come together at the same place, at the same time, and not knock each other out of the way. I can see them all collectively, simultaneously, because of their wave-like character. So in order to rationalize the way that electrons were behaving in atoms, scientists came to the seemingly crazy conclusion that they weren't bowling balls or spheres of matter, particles at all, they were waves. And only when we treated them like waves were we able to rationalize how an atom could be held together. Really weird. Now, the third important premise of quantum mechanics is that energy is not continuous. Energy is not like a ramp. Energy is like a staircase. And I have another cartoon to, I thought I had another cartoon to show you that. I don't know, I thought I did, but I think I do on my slides I posted. But what we can treat this like now then, if I think of what do I mean by continuous energy versus non-continuous energy? Think about when I'm throwing a baseball, and the baseball has energy. And the harder I throw it, the more energy it imparts into someone when I hit them with it. And essentially, I can throw this baseball at any speed I want. So the energy I can put into the baseball is continuous, meaning I just throw it a little bit harder, it's going a little faster and has more energy. A little bit harder, a little bit faster, and a little bit more energy. So I can stepwise increase the amount of energy that is contained in the baseball. But what I'm saying is true for electrons. Instead of the energy coming in waves, it comes in steps. So the electron can go up in energy and up in energy and up in energy, not any amount it wants, but only certain amounts of energy. So that's where the word quantum comes into quantum mechanics. There's a quantity of energy that's allowed. So the quantity of energy that's necessary to get me to the next level has to be put into it before it gets to the next level. I can't just take a number and continuously increase it. I have to put a chunk in that fits the space of the steps of energy that are available for the electron. So quantum mechanics is bizarre and weird, and we're not going to even mention it any more than this, but it took a lot of scientists a lot of time to come to the conclusion as to how quantum mechanics works. What we are going to do, though, is we're going to return now to the atom, and we're just going to look globally at atoms. And in particular, we're going to look at combinations of, big piles of the same atom together. And what we said, a big pile of the same atom together is, we call it an element. So if I have the element sulfur, I have a collection of the same types of atoms in the pile. If I have the element gold, I have a collection of the same exact kinds of atoms in a pile. Now, it takes a huge pile of these before they are discernible, because each individual atom is not visible to the naked eye, of course. I have to have a large number of them before you can even see it. How large? I would say you need 10 to the 20 atoms. 10 to the 20 atoms of material before you can even see it. Now, if you had a microscope or you had some device that allows you to increase your optical ability, yes. But to the naked eye, you need, I would say, 10 to the 20 before you can see it. Now, how many is 10 to the 20? That's 1, 0, 0, 0, 0, 0, 0, 0, 0, 20 zeros. That's how big that number is. And that's a heck of a lot of atoms before it becomes discernible. Okay, so what I'm showing on this particular slide are some of the original symbolic representations that early studiers of materials used to represent various things. Now, I want you to first note that I have some Greek listed ones and I have some European listed ones. And what I want to point out to you is that I in no way, shape, or form intend that you have to memorize the symbol that was used for gold and the symbol that was used for stone in ancient Greece. That is not the intent of this slide. I'm just showing you these here for a couple reasons. And mainly to show you, first of all, that there was some, first of all, lack of understanding of just what elements were, because many of these things are not elements at all. Gold certainly is, silver certainly is, but vinegar is not an element. Vinegar is a combination of elements. It's molecules. Stone is certainly not an element. stone is very complex and can contain, depending on what kind of stone it is, a wide variety of elements. So salt certainly as well is not an element. It's a combination of, if it's the normal salt that we use, of two elements, sodium and chlorine. So many of these things were not really understood as being elemental at the time these kinds of symbols were devised. The second thing I want to point out to you is that you should note that these symbols are very cryptic. And what I mean by that is there's no real logic to what the signs appear as. And there's good reason for them to be cryptic. If you recall, I talked about the fact that when early on people were using chemistry, they were not doing chemistry to understand the working of the world. Early on, people were doing chemistry to either dupe people, to frighten people, to entertain people, or for some means other than to really understand what was going on. So if you knew that you mixed a certain amount of this and that, and you could put it in a pile, and when you put a spark on it, it would make a big flame, a big flash, a big puff of smoke, and a lot of noise. And when you did that in front of people, they would go, oh, he's a witch, or he's a wizard, or he has supernatural powers. You certainly would not want to share with others what you were doing in order to make that occur. So the symbolism you would use when you wrote down the formulas for the mixtures you concocted in order to do that were naturally cryptic. So there were a lot of cryptic symbols that the alchemists employed so that they could keep their things they were doing a little secret. Now, the other thing you can certainly recognize if you look at these symbols is that if you saw a page full of these, you would certainly begin to wonder if it's not satanic, if there's not something deeper spiritually behind what you're conveying on this paper other than an understanding of the nature of matter. So it's easy to understand why the early practitioners of chemistry and material science, it was couched in wizardry and supernatural stuff more so than it was in understanding the fundamental behavior of the world around us. So this is the beginning points of our trying to keep record of materials and how we use materials in chemical processes. And again, I would conclude by saying they are abstract and in many cases kind of scary or cryptic purposely so that you could keep the things you were doing secret. Now let's move ahead to the time of Dalton. This is a few hundred years later. Now the symbols are still, I would say, notably cryptic. They're not quite as scary. Okay, they kind of got rid of some of the satanic look to them. But now I want to point out to you that they are beginning to be systematized. Now, what do I mean by systematized? Is just notice what the symbol for hydrogen is. Then notice, of course, what the symbol, it's a circle with a dot for hydrogen, and notice the symbol for oxygen is just simply a circle. Then look on the other, or at the bottom, and notice what the symbol for water was. The symbol for water was a combination of hydrogen with oxygen. So they're beginning to figure these things out. Now, also, we should point out that they were wrong, because, of course, I think even your mom and them know that water is H2O. The way they're drawing the symbol for water, it looks like they thought it was made of hydrogen with one oxygen, not two hydrogens with one oxygen. And notice ammonia is a combination of hydrogen and nitrogen. It turns out that actually ammonia is nitrogen with 3 hydrogens. So there should have been 3 circles with dots if they really knew the formula for it. Now, other things I will point out to you is they had carbon, they called it carbonic oxide. We would have called that carbon monoxide. Then they had carbonic acid, which is what we would have called carbon dioxide. Notice carbonic acid has a formula of a dark circle with 2 light circles, and that would be carbon dioxide. Now, they were calling it carbonic acid. And interestingly, if you dissolve carbon dioxide in water, it does make carbonic acid. So maybe they were more familiar with the dissolved form of carbon dioxide than they were with the gaseous form of carbon dioxide. So that's why it was called carbonic acid. Sulfuric acid is the same sort of idea. If you'll notice what the symbols of sulfuric acid are, it's a sulfur in the middle attached to 3 oxygens. In actuality, sulfuric acid has 4 oxygens, a sulfur, and 2 hydrogens. But once again, if you were to dissolve what they're showing in water, then you would have the correct formula for sulfuric acid. So this is what we would call sulfur trioxide, and sulfur trioxide dissolved in water does make sulfuric acid. So the point we want to take from this is that by the time of Dalton, even though the symbols remained somewhat cryptic, what was done was that they were being systematized so that they now kind of made sense, and they were taking away any satanic or any wizardry-like connotations from the cryptic symbolic representations that had been used a couple years before. Okay, now, what about modern symbols that are used? Well, modern symbols are transparent entirely. We use letter symbols to represent the elements. Hydrogen is just H, helium is He. Now, why would we do something like this? Because it gets tiresome when you have a complex chemical reaction to write the word hydrogen. We're just going to put it down in H, and we're all going to understand that we're talking about hydrogen. And of course, for helium, well, we could have used something else. The name helium comes from Helios, which was the Roman god of the sun, because it was noted when people were able to discern what these things were made of, was that the sun was made up of helium. There was a lot of helium in the sun. So that's where the name of the sun came from, or the name of the element that is mostly what the sun is composed of, was used as helium. And since H was already taken, they gave it the symbol He. Nitrogen is given a symbol N, oxygen is given a symbol O. So these are now completely transparent, completely understandable symbolic representations for the various elements. Okay, now, many of them are named after scientists. Now, again, what I want to point out to you is I'm showing you 3 of them here on this slide, named after Marie Curie, who discovered some radioactive elements, and of course, Albert Einstein, who did just a ridiculous number of crazy things, and Enrico Fermi, who helped us make atomic bombs, but he did other things too, but so he gets an element as well. Now, most of these elements are down toward the bottom of the table with high element numbers, and we'll talk about what it means to have a high number when you're an element later. It means that many of them are actually artificial. Many of these are man-made elements, and so the people that made them often took the honor or right to give them any name they want, and many of the people who made these elements gave them names that were related to their scientific heroes. Okay, so again, do I want you to know these elements and their names and who they're named after? No, this is really just to tell the story of what we're doing here, more so than these are things that I want memorized by you. That's, believe me, I don't even know the names of all 115 elements in the periodic table, and I'm a practicing chemist, so I don't know why you should know them just because you're taking this class. Okay, now just those some other interesting things where many of the names came from. A lot of them came from the fact that they were used in ancient Rome, and so they have their Latin names. And the symbols that are used are taken from their Latin names. Like copper in ancient Latin was cuprum. So we still use Cu for copper because that's what the Romans used for copper. Uh, what else do we have here? Au was aurum. That's what the Romans called gold. So the symbol for gold is Au instead of maybe G. Ferrum is what they called iron in Latin. So Fe is the symbol for iron rather than being I or maybe IR or something like that. And Pb is the symbol for lead, and that is given the name, as you see there, plumbum. And then we have, I have a name for silver, and I have a name for tin. So all of these elements were quite familiar to the Romans, and they borrowed their symbols from their Roman names of choice. Okay, the one I want to focus on for a moment, you know I like to tell stories. So I got to tell the story of plumbum. Plumbum is lead, and what plumbum was used for in ancient Rome was there was plenty of it around, and it turns out it was very durable, very heavy, very sturdy, and also very malleable and formable. So plumbum, it turns out, much like gold, can be easily shaped. As a matter of fact, I told you early on that they tried to transmit lead into gold because lead seemed just like gold. It was really heavy and dense, and you could pound it out and make it into shapes really easy, just like you could do with gold. It just didn't look pretty and shiny. So it just seemed like they were so much the same that you should be able to easily make one into the other. But what the Romans did with it was they made all kinds of shapes out of lead, including one of the most popular things that came about near the end of the Roman Empire. And near the end of the Roman Empire, what the rich and powerful people of Rome desired was something that kind of makes sense. They wanted indoor plumbing. They got tired of taking a dump in the cold. They got tired of having to go down to the well and haul water into their house. They literally wanted to run pipes from the water source into their house, just like we'd like, and they wanted to have plumbing. Well, they needed a conveying device that was durable and strong, but also bendable and shapeable so that they could run plumbing in their houses. Well, to run water conveyance. So this became known as plumbing because they used lead to form pipes and run them through their houses. Now, as you can imagine, this was only a status symbol. Not everybody could have plumbing in their house. You had to be rich and powerful. So only the richest merchants, the senators, the leaders of the armies, all these people built indoor plumbing in their houses. And of course, if you also know the story, lead ain't the best stuff. So these people began to drink water from the lead pipes that were running through their houses. And there's much conjecture that the elite of society of Rome, who all had this indoor plumbing, became ill and feeble and unable to carry on the things they were doing. So this was one of the factors that many people believe contributed to the ultimate demise of the Roman Empire, because all the important people had this lethal water source for a status symbol in their homes. So that's kind of a cool story. And of course, we can recognize immediately that the word plumbing comes from the fact that the Romans at the time were using their lead pipes in their buildings. Okay, so what we're now going to do is we're still talking a little bit about the structure of the atom, and we're going to systematize our idea of the structure of the atom. And what I'm going to note is that the roadmap of chemistry, the source of all understanding of the behavior of the materials that are the building blocks of matter. This is all put together in what is known as the so-called periodic table. So the periodic table expresses the ideas that culminate in our understanding of matter. Now, the periodic table, I'm sure you've seen it before. I'm showing it on this particular slide here. And it is always laid out in this ubiquitous form, always. When you see the periodic table, this is how it is always presented to you. Now, what I want to make clear to you is that this was not chosen from a focus group. They didn't say, all right, let's look at a catchy way to lay out the elements so that people will recognize it as our chemistry trademark. So that whenever people see this, this is the way we want to portray it. It always has this same shape, and it always has this same arrangement. Where, why don't they just like list them in columns with equal numbers of elements in each column? Why is there all these gaps and turns and bends in the table? Well, it turns out this is solely due to the way electrons pile up around the nucleus. It turns out that this table fits the behavior of collecting electrons together perfectly. And it took a very, very long time to unravel this so-called structure of the periodic table, but it has been done so. It took maybe 100 years or so, so that we lay out the elements invariably in the shape that we see in front of us right here. Now, each box in the table, and there's about 115 boxes in the table I have in the room and the table I'm showing on this slide, are both dated. They are not the absolute latest periodic tables. The latest periodic tables go all the way across the row that's incomplete at the bottom. They go out over to element 114. So that's where we are now. We have 114 elements, more so than the ones that you're seeing here on the slide, or if you're in the room, the one that is on the wall. And each box has its own symbol. There's a different symbol in each box because each box represents a different element. So there are essentially now 114 things that are identified as elements, 114 natural building blocks of nature. Now, the other thing I want to point out to you is that these boxes are sequentially numbered. They begin at the upper left-hand corner with box 1. Then there's a big gap, and in the same row as box 1 is finally box 2, but I want you to notice there's a big space. Box 1 is in column 1. Box 2 is in column 18. Now, we're not going to delve deeply into why, but let me just suffice it to say it has something to do with the way the electrons are piled up around the nucleus, that the helium element in box 2 fits better with its cousins in the same column. And that's why it's piled, it's shoved way over there. Hydrogen, on the other hand, behaves similarly to its cousins in column 1. So there's something about the chemical behavior of the elements that decides which column that you will pile them up in. But in any event, the first row has elements 1 and 2. Then I come to the second row. It begins with 3 and 4. Then there's a big space. Then it concludes with 5 through 10. So then I have a carriage return again in the periodic table. And I go with element 11, which is sodium. In the third row, in the magnesium, and then a big gap again. And I go across through the element argon in row 3. Okay, now here is the important thing that I want you to recognize, and actually I want you to know this. Each box in the table represents a different element, and what makes each element different from each other is the number of protons in its nucleus. Every element must have a different number of positive charges in its nucleus. And as a matter of fact, that is what is known as the atomic number. The atomic number counts the number of protons in an atom, and the atomic number is the value represented by the box number of the particular element. So it's almost like what we could say is redundant information. Box number 1 has an H in it, and at the top of it is the number 1. All atoms of hydrogen have 1 proton. Box number 2 has a symbol He that says it's an element, helium. Helium element is made up of helium atoms. All helium atoms, 2 protons in their nucleus. And I can just continue this anywhere I want in the table. Gold, element 79. Gold has 79 protons in its nucleus. Now, what you should notice is that no 2 boxes have the same number. That's because all elements are unique in the number of protons that they possess. Now, I want to point out to you this very important fact. It is only the protons which differentiate one atom of an element from another. Atoms of different elements may have the same number of neutrons. Atoms from different elements may have the same number of electrons. But atoms from different elements always have different numbers of protons. Okay, so please keep that in mind. That's the rule for differentiating one type of element from another. Now, another thing I want to point out to you is as you get down to the bottom of the table and the number of the box becomes very large, that of course means the number of positive charges in the nucleus becomes very large. It turns out that there's a limit to what the nucleus can stand. There is a limit to how many positive charges you can pack into the nucleus. What happens is as you try to get too many in there, the nucleus becomes unstable, and it's no longer an element that has permanent ability to hold together. We have a fancy name for that. We call it radioactive. If you have a radioactive element, it has an unstable nucleus. And the reason the nucleus of a radioactive element is unstable is that it does not have a stable balance of protons and neutrons in its nucleus. Everything in the table from uranium on is radioactive. Uranium is element 92. Everything after that has too many protons for the nucleus to hold together correctly, no matter what number of neutrons you mix in there. Now, I want to point out that that's really not the beginning of radioactivity, though. There are radioactive elements in the table before 92. Most notably, that would be radon in the bottom right-hand corner. I guess that's 86, excuse me. 86 is certainly a radioactive element as well, but there are everything for sure after 92 is radioactive. As a matter of fact, I believe the last stable element that is not radioactive is lead. Element 84 is the last one that is not radioactive. Everything after that is radioactive. Now, what does it mean to be radioactive and where did that name come from? This is when they could detect radiation coming from the nucleus. As the nucleus doesn't like its structure, it naturally and spontaneously undergoes a change. And as it undergoes this change, it emits energy. And that energy could be detected as radio waves, not just in the radio frequencies, but in a wide variety of frequencies like X-rays that we still use to take pictures of our bones and things like that, like gamma rays, and like many other regions of the electromagnetic radiation. With that in mind, though, they are called radioactive because they would give off this radiation. And it turns out this radiation, if you expose yourself to it for long enough periods of time, ain't really the best stuff. So elements eventually become unstable. There's a limit to how many protons you can pack in, and it doesn't matter then how many neutrons you put with them. They're not going to be able to stay the way they are. They're constantly going to be undergoing change. Now, the other thing I would point out too is that uranium is the last naturally occurring thing. It is radioactive, but we could dig it out of the ground. Every element beyond number 92 is artificially made by humans in a laboratory. So that's another fight that people have over who made this element first, who gets to claim that they discovered this element because they made it. They made rules that said if your element doesn't last in a jar for so many fractions of a second, then you can't count it as a stable element. So you can't add it to the table. So there's a bunch of rules that were made as people began to fight over seeing who could manufacture these fleeting elements that don't last anyways. Because as soon as you make them, the ratio of protons you're putting in there are unstable, and so they immediately begin to fall apart anyways. All right, so another interesting thing, again, to point out about the shape of this table is that they're piled in these ubiquitous columns. You always see them piled in these same forms because they try to group the elements in terms of their reactivity. All elements in the same columns are going to undergo similar chemical reactions. They're going to enter into combination with other elements in exactly the same ratio as everybody else in their column. So there's some rhyme and reason to the pattern. And this is why the name says it all. The periodic table. When we say periodic, what do we mean? It's kind of like going around the circle. Going around a circle is periodic, meaning you come back to the same place as you go around the circle after a period of time. So what we're saying then with the elements, you come back to the same place after a period of time. What do I mean? Let's just take column 17 of this table, for instance. And let's look at combining the elements in column 17 with hydrogen. The top of the table is F, which is fluorine. And when hydrogen combines with fluorine, it makes HF. One H combined to one F. When chlorine combines with hydrogen, it makes HCl. one hydrogen to one chlorine. When bromine, the element underneath chlorine, combines with hydrogen, it makes HBr. When iodine combines with hydrogen, it makes HI. Everybody in column 17 has sort of a definite proportion of combination with hydrogen. But now let's move over one. Let's go to column 16, which of course is headed by oxygen. When oxygen combines with hydrogen, I think we know, it makes H2O. Remember, the ones in column 17 make HF, HCl, HBr, HI. The ones in column 16 make H2O, H2S, H2SE, and H2TE. So they all, again, behave similarly under combination with H. Now here's where the word periodic comes into this. Let's just think of the numbers of the box. You're increasing the protons. Increase, increase, increase. But you come back around. Remember I said periodic is like going around a circle, and you come back to where you start. So when you have 8 protons, you're at oxygen. But then when you come to 16 protons, you have sulfur. And when you come to 34 protons, you have selenium. But you periodically are coming back around to the fact that they form H2O, H2S, H2SE. So that's the periodic, and that's why that word periodic is present in the table. There's a repeating pattern of chemical behavior for the elements in the same column. So that's the magic of the terminology that we're using for the periodic table. Okay, so let me say something else about the structure of atoms. We're going to also define what we call the mass number. The mass number counts the particles in the nucleus. And if you remember, and this is again something that we should know, and I'm probably pretty sure most of us do know, that the nucleus consists of the protons and the neutrons. So when you have the mass number, we count the number of protons and neutrons. And why it's called the mass number is from an earlier slide, we talked about the fact that these are way more massive than the electrons. So once you account for the protons and neutrons, you've accounted for all the mass. The electrons are so light that they don't contribute significantly to the mass. Just the things in the nucleus contribute to the mass. So the mass number is defined by the contributions of those two particles. Okay, now as general trend, there's a 1-to-1 ratio of neutrons to, I left off the word proton, at least on my slide. I thought I fixed all these boo-boos I made. There's a 1-to-1 ratio of proton, and I left off the word proton. It should say 1-to-1 ratio of neutron to proton. So what does that mean? Helium is element 2. It has 2 protons. That's what the 2 means. It has a ratio of 1-to-1 in protons and neutrons. So guess what? Heliums have 2 neutrons as well as 2 protons. Lithium is in box 3. Lithium has 3 protons. Lithiums have 3 neutrons. Beryllium is in box 4. Berylliums all have 4 protons. Berylliums all have 4 neutrons. So essentially, to hold the positive charge together in the nucleus, you need about as many neutrons as you need protons. Now, when you get to the heavier ones, some have a 1.5 when you get to the heavier ones. Okay, so like down by lead. lead has 84 protons, and it has roughly 84 plus 22 or 106 neutrons, 1.5 as many neutrons as it has protons, because it's starting to get difficult to hold all that positive charge together. Now, an isotope turns out to be an atom that has the same number of protons, but it has a different number of neutrons. And most elements exist in isotopic forms. The proton is what defines the element as a particular type, and that's where the positive charge lies. The neutrons are just kind of gluing it together. So in slight variances, you can have slightly different number of neutrons and still glue the positive charges together. So isotopes occur when you don't have as many neutrons in atom A of an element as you have in atom B of an element. They're exactly the same in terms of protons, but they differ slightly in terms of neutrons. So if atoms have the same number of protons but different number of neutrons, a fancier way of saying this is that isotopes are atoms that have the same atomic number, but they have a different mass number, because the atomic number counts the number of protons, the mass number counts the number of protons plus the number of neutrons. So all atoms that are isotopes of the same element have the same number of protons for sure, if they're going to be the same atom, but they can definitely have different numbers of neutrons. All right, so another thing that we should keep in mind is that when atoms become charged, they now become sticky. I can now start to stick them together. And generally speaking, atoms that are neutral don't have points of stickiness towards one another. Neutral atoms are atoms that have zero net charge. And as I talked about early on, this is what J.J. Thomson was working with. He had a sheet of gold, but the gold had no net charge because the gold sheet that he had was neutral. The gold sheet that he had equal numbers of protons and electrons. Now, if you make an atom charged, you can make it charged one of two ways. The first way you can charge an atom is to make it an anion. And what an anion is a negatively charged atom. And of course, negative charges are electrons. So if I'm going to negatively charge an atom, I add electrons to the atom. So when you drag your feet across the carpet, as I talked about last time, the carpet begins electrically neutral. You begin electrically neutral. But as you drag your feet across the carpet, you drag electrons loose from the carpet and they pile up on you. They don't just roam freely on you, they attach onto an atom. So you are forming a bunch of anions in your body when you drag your feet across the carpet. After you build up too many anions, the charge becomes unstable and it makes a little spark and redistributes so that everybody becomes electrically neutral again. So when you form a negatively charged atom, we call it an anion, and an anion is made by adding electrons to an atom. Now, according to the way the universe works, anytime you make an anion, you simultaneously make its opposite. You simultaneously make a cation. Now, this word looks like it might be pronounced cation, but it's cation. A cation is positively charged. So, cations are positive, anions are negative. Most atoms are neutral. Anytime you form an anion. Somewhere else in nature, you simultaneously form a cation. You must. The electron can't be conjured out of thin air. When you make something negatively charged, somewhere else something became positively charged. And vice versa. If you make a cation, simultaneous to making a cation, somewhere else you're making an anion. Because in order for something to be positively charged, it has to now have an imbalance of charge. The charge it lost didn't disappear. The charge it lost went somewhere else, so something else has become an anion. Now, the last thing I want to mention today is that when you make a cation, you never, and I will repeat, ever make a cation by adding positive charge. Cations are only made by removing negative, never adding positive. Now, do we have the technology to add positive? Yes. But in practice, does that occur? Never. Why? To add positive, you'd have to be shoving protons into the nucleus. When you shove protons into the nucleus, I don't know if you know what that means, that would be nuclear fusion. And what does nuclear fusion? The sun. The sun does nuclear fusion in order to generate all the crazy energy that the sun puts out. We do not have the capability of doing nuclear fusion, at least on a lab bench. The craziness of our scientists, we figured out how to do it, and we made hydrogen bombs. So in typical processes where positive charge is being formed, is not being formed by adding protons, it is being formed by removing electrons. So when I drag my feet across the carpet is becoming positively charged because it is losing electrons. Okay, I think I'm quitting for the day. And I think there's something up with my slides. I think maybe the slides you have might have looked slightly different than mine because I thought I changed some slides and posted some different ones, put some other admonishments in. I have to investigate that as another one of my screw-ups. The way life goes. So remember to complete your activity online, and I'll be posting another activity online, and I'll see you next week.